first MICCAI. So I'm not a person to study medical science, so I don't actually understand like medical imaging or not. So, but it's actually my great pleasure to be here. So I very much thank the community to invite me because I learned quite a lot from you guys about like how complex the medical science is and kind of like the critical problems you are trying to solve. So maybe one day my life will actually be saved by your technologies. So I have a full respect to your research. Today I'm not going to talk about, say, medical imaging or some other things. I'm going to talk things purely on machine learning, but I hope I won't bore you with kind of theory things. I will try to explain things in, figures, and you definitely let me know that if you don't understand anything. So ask me questions anytime if you want. Okay? So I want to first give some sort of like philosophical discussions on why we actually need uncertainty estimate. So there are tons of different arguments. I basically just group it into two parts. So first, definitely like, do we actually have big data in your research? So deep learning has a great success because people argue that we can actually feed in many data points to train your deep learning model, and the number of data points increases, the more accurate your model is. But if you think about the actual meaning of big data, if you have a big difference, sorry, I should go back to, okay, so the big difference between these two things, you can basically see the difference. So if you only have some very low dimensional data, and you have 1,000 data points, I can claim this is a big data setting. But if you think about the cases like, say, medical imaging, where the intrinsic dimension of your data is like 1,000 dimensions, and then you only have 1,000 data points, I wouldn't claim this is a big data setting, okay? And also, it also depends on like the size of your model. So if you think about you have a super small neural network, let's say just one hidden layer with 50 units, then the number of parameters there is kind of like 1,000-ish. And in this case, it would be very different from like the, say, in the big neural network setting where you have, say, many layers and you have billions of parameters. So in this case, say 1,000 data point for the small neural network and 1,000 data point for a big neural network is definitely different. Although in the end of the day, you will actually see that when you actually have a super wide neural network, you have some other less intuitive things on this kind of big data setting. Okay, so that's the first argument. The second argument is actually whether we have a perfect model to do our machine learning problem. So first, training data distribution equals to test data distribution. This is one of the biggest lies in machine learning. Okay, although we as kind of doing machine learning and doing theory, we often assume this. In practice, it is not, and I think maybe in your medical applications, this is most of the cases, training data distribution is not equal to the test data distribution. So that basically means even when you have a perfect model on the training data, you might not have kind of like the right answer or right predictions when you apply it to test data. Okay? So now let's just pretend this biggest lie is true. Okay? Now, if you have test data equals to training data, do you actually get a 100% accuracy with 100% confidence? Which means, do you actually learn the ground truth function given finite number of data? And usually this answer is no. So you definitely need some sort of like, say, confidence estimate or uncertainty estimate to tell, okay, am I confident on my answer on the test data? Okay, lastly, the labeling process can be noisy. I'm trying to come up with a medical example. So the example I come up with is kind of like when you ask some sort of doctor to say give the prediction on what kind of disease this person is. Different doctors may have different opinions on that, right? So this basically tells you that you have noise or even disagreement in the labeling process. So in this case, you also need to tell like your system also need to tell like how confident I am to predict this person have disease A and disease B and so on. Okay, so these are just a few examples that tells you, okay, you really need uncertainty estimates when say any of the thing is relevant in your application. Okay, so let me try to briefly introduce like what we mean by uncertainty. So this is a super simple example. Let's just imagine you are flipping a coin. Okay, so first, you have the composition of two uncertainty, epistemic uncertainty, or people call it model uncertainty, and also aleatory uncertainty, or data uncertainty. So in one sentence, epistemic uncertainty tells you how much I believe that this coin is fair. Okay, you can do many experiments to actually get the kind of your belief on that. So that basically means this thing relates to the population of your experimental result. And you can basically kind of get more and more confident when you have more experiments. Another thing, aleatory uncertainty tells you, okay, what's the next coin flip outcome? So this thing only relates to, say, the experimental outcome for each individual experiment. It is not related to the population. So, and this thing is not reducible because, even when you know this coin is kind of fair, 100% confident, the next coin flip, you don't actually know this is kind of like a head or tail. Okay? In terms of like the distribution shift, it is kind of like asking a question like, am I still flipping the same coin, right? So when you apply a model to the test data, you need to actually think about whether this is true or not. Okay, so in this talk, I'm not going to talk about this. I think there will be some other talks talking about the recent research in your area to do distribution shift detection. I will focus more on these two parts, epistemic uncertainty and aleatory uncertainty. Okay, so in this conference, I've seen somewhat doing this uncertainty estimation with some sort of like Bayesian neural networks. I'll just give you a very brief recap on what we mean by Bayesian neural networks. So in this case, I'm considering classification, and I'm going to classify different types of cats. So if you are going to build a neural network to do that, then the neural network will have some parameters, and then you have some input. You feed your input through some neural network, and then finally add in the softmax function to give you kind of like probability of the assignment for which type the cat is. So this thing will actually kind of capture the aleatory uncertainty. Okay. Now, how do we actually model the epistemic uncertainty, right? So instead of using a point estimate for W, I'm going to say I will have put a prior distribution P of W over the weights, and then I have some sort of observation from data. Now I'm basically just use Bayes' rule. I need to compute the posterior distribution given the data set, right? This is basically just Bayes' rule. So if you can do that, then in prediction time, instead of using one point estimate or one training neural network to do prediction, I'm going to average over kind of like all possible neural networks where the distribution we are going to average over is the posterior distribution. So this is the exact form if you're going to do Bayesian predictive inference. But definitely in practice you cannot do that because integration is one of the most difficult computation problems. So in practice, what people do is first I find some approximation to the exact posterior distribution. So either via Bayesian inference, or maybe the best kind of like the Monte Carlo dropout, or some MCMC method Markov chain Monte Carlo. So if you can do that, then in prediction time, instead of also you're going to replace the exact posterior with the approximate posterior, and also you're going to do one more step to kind of mitigate the difficulty of integration, which is to do Monte Carlo sampling. You're going to get some samples from your approximate posterior, average over it to get kind of like the kind of approximate Bayesian predictive distribution. I'm going to say a few words about these say inference methods. So maybe you guys know the paper from Yinzhen, so he's one of my previous lab mates. So he had this kind of derivation on like say doing dropouts in training time is kind of like doing some sort of like approximated Bayesian inference training, and in that case you can also argue that why you want to do dropout in test time, because it essentially tell you that dropout represents some sort of the mixture of delta distribution for this Q, and then in prediction time you just sample from it. But the MCMC method is also similar. MCMC methods will basically just construct a set of points, and then you're going to use this kind of say the set of points to approximate the posterior distribution, and in prediction time you just use those points. So I would actually recommend you to check out the MCMC literature, because so there is recent methods called stochastic gradient MCMC, which is actually almost as fast as, say, Adam or RMS probe as you would use. So I would encourage you to check out the stochastic gradient MCMC institution. Okay, so in terms of the empirical evaluation for the uncertainty estimation, so basically if you're going to summarize it into one sentence, then it tells you model prediction with 70% confidence should be correct 70% of the time. Okay, so this is just one sentence summarization of the uncertainty estimation. So existing methods basically just follow this sort of principle. This is expected calibration error, or for example, like this figure, basically just plot that the x, maybe you can't see it, but I will just talk through it. So the x-axis just plot the uncertainty estimation or the confidence from 0 to 1. The y-axis plots the accuracy. So that means if you have a calibrated model, it should be kind of like this x equals to y line, right? So then you can basically just plot this say curve by doing this kind of bin estimation, and then see how much this curve is kind of close to the ideal kind of like x equals to y line. Okay? So similarly, in the regression cases, you can also plot like say the 2 sigma regions of your prediction, and 2 sigma region basically will correspond to say 95% confidence. So then you can basically just see, okay, whether your ground truth observation lies in this kind of say confidence band 95% of the time. Okay, so that's similar. But these two figures, basically, it only evaluates the uncertainty, or maybe I should say epistemic uncertainty plus aleatory uncertainty in total, right? So now the question here is, how do I actually evaluate these two uncertainties in separate way? Or do I really need that, right? So first, as I said, aleatory uncertainty tells you the variations in the next experiment. So that means you cannot reduce it, but you can basically just collect data and then get some sort of empirical statistics and see whether your model whether the uncertainty estimate, the aleatory uncertainty estimate from your model matches the kind of empirical distribution. So this means it is very easy to evaluate whether your aleatory uncertainty estimate is calibrated or not. But the epistemic uncertainty is actually much harder. Right? So first, if you think about this counterintuitive example, so let's say you are lucky enough, or you have a super smart method that with finite number of data points, you actually get to the ground truth. Then in that case, you can actually say that, oh, I 100% believe that this is ground truth and only model aleatory uncertainty. And in this case, the total uncertainty is still good. You still have this right kind of calibration, right? But the problem here is you have almost no chance to get it with a finite number of data points. And also, the way we evaluate epistemic uncertainty is kind of much in debate, whether we should use probability theory to do that, or we should use some other things, because some people might care about, say, optimistic estimates of the epistemic uncertainty. Some other people may actually care about the worst case, right? It really depends on your application or like your belief or your kind of safety requirement to tell, what kind of epistemic uncertainty I want and how that is calibrated or not. So in this talk, I'm not going to talk about like the calibration of epistemic uncertainty because there is no kind of say gold standard to do it. But I'm just going to describe it in a qualitative way. So tell me if you don't agree with me. But I think the quantitatively epistemic uncertainty should be low when it's close to the data region, and it should be high when you are far away from the data region, right? So that's kind of like the qualitative observation. Okay, so these are some examples I get from this MICCAI conference. I encourage you to check out. Okay, so before I go to the needs of this talk, let me just briefly talk about why we need epistemic uncertainty again. So I'm not familiar with the medical application, so unfortunately I can't say for that. But let me just say in general for these three applications that machine learning people are very interested in. So for example, like active learning or Bayesian optimization problem, where the setup is like this. You are doing some sort of scientific experiment. And I want to know, okay, given the previous result, what is the next best experiment I can do in order to kind of say get the most amount of knowledge from the experimental result, right? So in this case, it tells you that you actually need to first have some sort of estimate or some belief on the amount of knowledge you have acquired from your previous experiment. And in this case, you also need to evaluate, like, on those parameter search base you can do, which set of parameters now you are most uncertain about its outcome. So that's one thing you need epistemic uncertainty. The second thing is reinforcement learning now is super in hype, okay? So the fundamental thing for reinforcement learning is essentially exploration and exploitation trade-off. Exploration tells you, okay, I have some sort of state or I have some experiment I haven't done. I want to know whether if I do that, I will get a higher reward or not. Exploitation tells you that, okay, I've done those experiments. I know kind of the reward for that. I got some sort of stochastic observation of the reward for that. Now I want to see whether I want to exploit it to actually increase my total reward. So in this case, now you also need some sort of estimation of the kind of like your knowledge or kind of the uncertainty estimation for that in order to tell, okay, whether I should try more on exploration and whether I should now start to exploit. And if I'm going to exploit, which part I'm going to exploit. If I'm going to explore, what's the next experiment I'm going to do. Okay, that's reinforcement learning. In some sense, very close to Bayesian optimization. These two things are actually closely related. One thing I also want to point out is continual learning. So I think this is actually relevant to your community, the medical community, because you have data coming from different hospital, and also you are going to update your data kind of during time. So that you want a system that can be, that can upgrade it yourself without like just training from scratch, and then use this system to do all the tasks in an accurate way. So the trade-off here for continual learning is essentially how well you can learn for the future task and how well you can remember the previous task. So essentially this tells you that, okay, I need to have an estimation of the knowledge, and I also need to know how confident I am. Because if, for example, let's say you are going to do this with neural network weights. So if you are overconfident on the weight parameters you get from the previous task, then in the future time, you are not going to change it too much. You will probably learn the future task in a, say, worse way. But if you are kind of like, say, underconfident on the parameters you get from the previous task, then in the future time, you are likely to change it, and then maybe you actually do worse on remembering previous tasks. So I'm just listing the 3 applications that I think you need epistemic uncertainty, and we actually need to do it in a kind of very good way. So yeah. So next I'm going to tell you some sort of that theoretical results we have. But before that, I want to pause for questions. Yes?
Can you go back to a few slides before? Okay, this one. Okay, just the previous. This one? Yeah, this one. Because at the last point, you say you explain what kind of the model uncertainty, what it is, right? I just wondering from this is low near data and high far away from data. So what different from the distribution uncertainty? Distribution shift you mentioned. What's the difference?
Okay, so the question here is, what's the kind of relationship between this kind of, say, argument and also the distribution shift problem, which is kind of very prevalent in your world. So I think they are closely related to each other, because if you think, like in terms of the input distribution, if in the test time you are mostly observing the input in kind of like the faraway region, then essentially your input distribution actually changes, right? So that is relevant in the kind of faraway region.
But how you can separate if you say there are 3 types of uncertainty, the data model and the distributional uncertainty, right? If you try to separate them, but it looks like these 2 is correlated. And kind of
so these 2, I think it's correlated, but there are some differences. Because test time, you can actually see like, you need to do some sort of population statistics in order to evaluate whether you have a test distribution shift or not. Because if you only show me 1 data point, say 1 test data point, this test data point has kind of like almost 100% probability to be different from the training data point you will see. But if you only use one data point, you cannot tell in a very confident way. Now you have some sort of like out of distribution cases. You actually need to do some sort of many experiments in the test case, and then compare with, say, many results in the training case to do this on the proper two-sample test, or maybe just as to say, compare the result on these two sets in order to determine whether you are in the auto-distribution region. So let me just summarize what I'm saying. In order to test distribution shift, you need to do it in a population level. For individuals, they are related, but I would say it is hard to run only one example to tell you now whether I'm in the out distribution or in distribution region.
Can I ask a question? So you talk about confidence a lot, but so correct me if I'm wrong, but confidence is not really like a term from probability theory, right? So it's sort of it's something we engineer, so we get a value between 0 and 1 that we can interpret, assume. But so do you know of any? I face this problem a lot. How do we get from a variance to this confidence? You know, is there like a principled way of doing it, or can we just?
I think there are tons of different definitions of confidence, right? Yeah. So I think you need to think about whether you want to adopt kind of probabilistic thinking of confidence, because besides probability theory, there are some other theories like fuzzy sets or like, say, beliefs in general, which might not be consistent with the probability definition. So if you accept kind of like the probabilistic definition of the confidence, then confidence usually arises in kind of like the frequentist, say, statistics part, and Bayesian part is kind of another way to describe it. I think in the probabilistic region, they are very similar. Okay, how many minutes I have? We're starting late, right?
We started a bit late. You have a bit.
We have 15 minutes.
15, okay.
Including questions.
Okay. I still have 15 minutes, so let me just go through the needs I want to show. So we talked about uncertainty, but previously I showed you the uncertainty estimate in weight space, right? So now I'm going to argue something else. I'm going to argue that in output uncertainty, what you need is to estimate uncertainty in function space rather than in weight space. So first, neural network weights is not some sort of scientific parameters you are thinking, right? If you are doing some scientific experiment, then you are definitely interested in the parameters because there are some, say, meanings for those parameters that you are interested in. But it is kind of like unknown or unclear that what are those neural network weights means in a scientific sense, right? So now you estimate it, you can get some sort of estimate from that, but you don't know what that means. Instead, if you think about like Bayesian neural networks where you sample weights and then to get propagate the input to the output, actually sampling a weight is equivalent to sample a function because the weight just parameterizes the function, right? So I'm arguing that we should use this kind of function space view to think about uncertainty. Because what we actually care, or kind of like the previous slides, the matrix I showed to you, is actually computed in output space, which is actually kind of like the function output. Okay, I'm basically just listing some problems of considering a weight space thing, but so they are not important to discuss. If you want to know more, we can chat. But I just made this point, right? Sampling some weight from the posterior distribution is equivalent to sample a function from some posterior distribution defined in function space. Okay, so now we see this kind of like multicolor dropout methods that is kind of say used by your community. We choose this kind of multicolor dropout because it is kind of cheap in the sense that, okay, you don't actually need extra parameters. Maybe you need some extra computation in test time because you need to do MC dropout for multiple times, but it's only one weight, right? One weight matrix. You have no kind of say memory overhead. So this is why we do multicolor dropout, and in the previous few years in the Bayesian deep learning community, we also take this view and then develop the Q distribution with the kind of like the idea that we want to first constrain the memory, which means I'm going to use simple distribution like vectorized Gaussians. And then in this case, we really made this method scalable to get some good accuracy. But now, the question I'm going to ask, and I'm going to a little bit answer for this in this talk is like, okay, we use because we have computational efficiency considerations, we use this simple Q distribution. So this simple distribution in Q gives you some distribution in function space. Do you really have some sort of like good properties of your uncertainty estimate in function space? So think about it yourself, okay? So now I'm going to talk about something called in-between uncertainty. So this thing is some sort of nickname we came up with. So what we mean by here is uncertainty estimation in regions between data clusters. So this is relevant to these two problems. First, missing values in time series. You see that you have some observations, but you have some missing values in some time interval. You need to impute that. So in that case, you need uncertainty estimate. And also, when you have, say, ambiguous input, that basically lies in kind of, say, the decision boundary between clusters. So that's also in-between uncertainty. Okay? So now let's see some sort of result we have. So I'm not going to read through these things, but let me just talk through with the cartoon. So the result we have, and we are going to present this in this year's Bayesian deep learning workshop, is that if you use, say, one hidden layer Bayesian neural network with random activation and this, say, Gaussian distribution as a Q distribution, then essentially you have these kind of, say, uncertainty bounds in the sense that the uncertainty estimate in terms of variance of the point in a hypercube is bounded by the variance function at the corners. Okay? So this is the first result, which means that if you use this type of, say, Q distribution in weight space, it naturally imposes a restriction on the uncertainty expression you can express. So this basically means that, okay, you are not going to get an arbitrary high uncertainty in the in-between region. There will be a bound. Okay? So why this happen? So a very simple figure to explain this, the intuition is like this. So if you think about radial activations, it's kind of like determined by some weights W to control the slope, and also the bias term that controls the intercept, right? So now, let's see how this fits to data. As we discussed before, epistemic uncertainty is good when it is low around data, and it is high when it's far away from data, right? So now we have these two data points. In order to get good uncertainty, we need to basically, fit all the possible functions through this sort of observation that gives you low epistemic uncertainty. But now in this in-between region, right, you have different type of radial function you can fit, like this one or this one. And in this case, you actually need to include correlations between W, the slope, and the intercept in order to retrieve different radial functions. So if you think about like the mean field approximation in the weight space, it basically just tells you, okay, they are uncorrelated. So you have no way to represent correlation between W and B in your approximate posterior. So that tells you you cannot get this one. Okay, so that's the intuition. The proof is actually quite involved, but I think the intuition is clear. Okay, so that's kind of like mean field approximation. Let's see MC dropout. So MC dropout things is kind of like very weird, but we have this result saying that, okay, again, this is one hidden layer Bayesian neural network with radial activation. Let's say you do MC dropout with any rate, okay? So now, if you have a set of points that they are the convex hull contains this point 0, then the value of the variance function 0 here is again bounded by the variance function at the point, this point. So again, this tells you, okay, if you pick Monte Carlo dropout, you cannot represent arbitrary, say, high variance function you want. Instead, there are some limitations that you need to be aware of. Okay, so this is the theoretical result. Let's see whether that happens in practice. So in this case, we consider this kind of, say, two toy setup where we want to evaluate in-between uncertainty. So the data clusters are here. They are clearly separated, right? So we use Bayesian neural networks with mean field approximation, MC dropout, and also compute a some sort of like ground truth Gaussian process regression with the right kernel. So you can basically see that, okay, these two methods the mean field variation inference, catastrophically underestimate uncertainty, right? This case you get some, but you still have some weird behavior around 0.0. But the Gaussian process solution can actually get to the right uncertainty. Okay? So I think this is basically just a result to tell you that there are some limitations in the approximate distribution you are going to use. So don't use that in a blind way. So whether that is relevant to your problem, or I should say, should I worry about this result because our previous result is only shown in, say, one hidden layer? So there are good news and bad news. The good news is, in theory, there is actually a mean field Gaussian distribution so that you can actually represent those kinds of nicely behaved variance function. Okay? The question here is, okay, it exists, but can you actually find it when you train neural networks, right? So we don't know yet. So basically, if you think about this kind of blue set is kind of like all possible Q distributions, and this kind of red set is kind of like the set of good distributions. We don't actually know whether the, say, Bayesian solution is in this set or not. So we decide to do some sort of empirical verification. So this is the same experiment again, but with 3 hidden layers. Okay? The result shows that, okay, you get something better, but you still have problems representing like the in-between uncertainty because it is not like, say, some relatively high uncertainty in between. It's still quite relatively low. Okay, so in summary, I think this result we are showing is that in terms of representing epistemic uncertainty, you really need to think about this thing in function space because the kind of relevant metric you are computing is actually using output. Also, when you pick the Q distribution in the weight space, think about whether that will give you kind of restrictions in representing output uncertainty. Okay, I will briefly go through the remaining slides. I still have this one. Okay, another thing is, so aleatory uncertainty can still be high even when your epistemic uncertainty is low. So you can think about this case, let's say your Q distribution is basically just point mass. But you can pick the point mass center W0 so that the softmax of your function output is some sort of flat, right? So in that sense, you still have, say, high aleatory uncertainty estimate from your model, but the epistemic one is low because essentially it is a delta mass around the point. But the problem here is epistemic uncertainty in decision boundary is still needed. So here I'm basically just showing you 2 examples. So you can imagine like a classification setup where the ground truth distribution is some sort of like soft labeling or hard labeling. Okay? So now you can basically see that the aleatory uncertainty is different. This is high aleatory uncertainty. This is low aleatory uncertainty. But you only observe finite number of data points, and you don't actually know which decision boundary I should put in between this region, right? And in this case, this sort of like uncertainty of the boundary decision boundary is actually represented by epistemic uncertainty. So that basically means it's still relevant. You need to do it. Okay? So before I end this talk, I want to just briefly mention why we want to do that and how we should do that. So there is a neat connection between Bayesian neural networks and Gaussian processes. If you want to know more, you can basically just check out this tutorial I gave a month ago. So essentially the idea here is, if you have a neural network, here you put a mean field prior on it, then if you have infinite number of units, just make it super wide, it will be approximately equal to a Gaussian process, which people love because it is a Bayesian non-parametric model. It has good uncertainty estimate. Recently, people have been extending this result by saying that, okay, it is true not only for one layer, it is true for any layer. So if you have deep Bayesian neural networks and you make kind of like all the intermediate hidden layers wide enough goes to infinity, you still have Gaussian process. And this is true for both fully cognitive neural network and also convolutional neural network. So this is essentially just showing some results. So these guys basically plot like the posterior from the Gaussian process and the posterior from the Bayesian deep neural network, which is simulated from HMC, the gold standard method, and then make the Bayesian neural network wide enough. You can see they are pretty similar or almost identical. So they have theoretical result. These empirical results also prove his point. So recently people have this on the neural tangent kernel also arguing something similar. So essentially the story here is if you have infinite number of units or network is wide enough, then you go back to this kind of non-parametric of kernel methods region where you have some sort of nice properties. We did some similar work by considering say, approximate inference in function space. So I argued previously that we need to be careful when we do approximate inference in weight space. So in this paper, which is ICML this year, we try to basically see whether we can say do approximate inference of Bayesian neural network in function space. So the idea is actually very simple. If you, as I argued before, prior over weights is essentially equivalent to prior over functions. So now you do have a Gaussian distribution over the Bayesian neural network functions. We are going to use a Gaussian process to approximate that Gaussian distribution, and then in prediction time use this GT to do inference. And also to kind of train a neural network, we are going to do the empirical-based approach, which means we are going to optimize the prior. So we have some results in the paper, but this is just an illustration of a regression problem. In this case, we compare our method of function space inference with dropout, the MC dropout method, and also kind of GP regression. So we essentially conclude that we have better function fits and also better uncertainty compared to these two models. Okay, I just want to summarize my talk. So in this talk, I basically talked about like say the uncertainty estimate in Bayesian deep learning. So I talked about like the decomposition of uncertainty, and if you want to use it, definitely use it, but also think about how to calibrate those uncertainty estimates, because if you're going to use it, you want to use it in a reliable way. Also, I spent some time to talk about our new theoretical results, so which tells you that, okay, when you choose your inference method, or kind of when you do molecular dropout or some other methods, you need to be a little bit careful on what is the consequence of the result in output space. Yeah, then I would basically just argue that we should think more about uncertainty estimation in function space, because what we really care is like the confidence of our recommendation to doctors, right? Okay, thanks. Yes?
You talked about this in-between uncertainty, but all your examples were one-dimensional. I wonder if the same limitations still apply in like a high-dimensional space, like images, where this in-between is less well-defined. Yeah, that's not.
Okay. Okay, so first, thanks for the question. So this theoretical result is agnostic to the input dimension. So this means this theoretical result is true for any input dimension. So it is not only like one dimension, although we show simulations in one dimension because it is easy to visualize. So how that is related to images, so let me try to think about it. Correct me if I'm wrong. Okay. So in the image segmentation problem here, because we are using CNNs, right? And CNNs, they are basically just processing patches. So that basically means, in some sense, you can think about the patches as input, right? So now, because usually the standard practice is to normalize, kind of standardize their data so that your input range is between some, say, -1 to 1, something like that. So that basically means you do have some sort of like clusters of your patches that is, say, somewhere, around -1 and somewhere close to 1. So I would say that, in the segmentation part, there will be some sort of in-between uncertainty there, because you can consider the patches as input, and your patches definitely look different, these different locations.
Thank you.
Do we have any other questions?
Thanks very much. Could you elaborate on why you think uncertainty is good for continual learning?
Okay. Right. So there are different types of methods for continual learning, actually. So one type of method is basically just telling you that I need my weights of the neural network to be flexible enough so that I can retrain it right? I can retrain it to basically adapt to the next task. But then if you just retrain it without some other regularization, then yeah, you can do very good things on the current or future task, but you completely forgot the previous task. So now the question here is, how do you actually do this continuous learning so that you first learn good future tasks, but then you still remember the previous task, right? So uncertainty here essentially just tells you that how confident you are on your previous knowledge, right? If you're confident enough, then maybe you should say, okay, I shouldn't change my current knowledge too much. Then in this case, you are restricting your parameters to some sort of very small region, so that the parameter won't change too much, and you wouldn't do the future task in a good way. Another thing is if you say, okay, I'm very uncertain, or say underestimate the confidence of my parameters, then you have a lot of rooms to change it. You can move it towards fitting the future task, but then now you have less good performance on the remembering previous tasks. I hope this answers your question.
Thank you for the answer. So that would be per parameter, right? And so I think if you have a very large network, it would be difficult. Then you would need to do some, like, estimate the variational inference for every parameter, not to do MC dropout. Would that work in an MC dropout setup? Because you won't get per parameter uncertainty estimate.
Well, I mean, so here's what I think. People do this sort of like uncertainty estimate in weight space because it's convenient, right? But if you think about it, what you really need is the knowledge about the underlying classification function or the underlying regression function, right? So that basically means if you have a representation of kind of like the uncertainty in function space, you can do it. So first, my claim is that doing this sort of continuous learning, the method is not restricted to, say, doing regularization in function space. Second, there are other methods to do continuous learning, for example, like, store some sort of key points from the previous task and then replay. And also like possibly grow your neural network, which essentially also corresponds to changing your belief of the candidate model or kind of like the candidate knowledge that you should apply to the future task. So I would say that uncertainty is important, but it is not the only factor that affects the performance of continuous learning.
Okay, thanks very much. In the interest of time, we have to move on to the next talk. So let's thank the speaker again for this great talk.